The conference room at Berlin's Reich Air Ministry in the autumn of 1939 exuded an air of quiet confidence. Luftwaffe technical officers had gathered to assess the capabilities of Allied aviation. When the discussion shifted to Britain's Rolls-Royce Merlin engine, dismissals came quickly. Oberon engineer Wilhelm Gundermann, while reviewing intelligence photos of the engine, made a note that would later appear almost comically misguided. He stated that the liquid-cooled design was operationally vulnerable and outdated. His colleagues agreed, confident that they had surpassed such primitive thinking. The German aviation community had come to believe that air-cooled radial engines were the future of military aviation. Their reasoning had some basis. Radials were more durable than liquid-cooled engines, which had fragile coolant systems and radiators. A bullet through a glycol line could cripple a Merlin-powered aircraft, while a radial engine might continue to run even after losing a cylinder. This line of thinking had shaped the Luftwaffe's fighter programs, from the Focke-Wulf FW-190's BMW radial to the continuing development of increasingly powerful air-cooled designs. However, there was something more at play than just technical preference. The German aviation industry had developed a sense of institutional arrogance during the 1930s, born from genuine advancements in aircraft design. They pioneered all-metal monocoque construction, created superior cannon armament, and even developed the world's first operational jet engine. When Messerschmitt test pilots flew the Bf-109 against the Henschel HS-12 in 1936, they produced what many considered the finest fighter aircraft in the world. Why would they need to learn from Britain's outdated liquid-cooled approach? Technical documents captured after the war revealed how badly the Luftwaffe had misjudged the situation. A 1940 report from the Luftwaffe's technical department characterized the Merlin as a design philosophy that had already been superseded by modern air-cooled technologies. The report criticized the Merlin's complexity, reliance on precise coolant mixtures, and the extra weight of radiators and plumbing. These weren't foolish men making poor assessments. They were experienced engineers following what seemed like logical reasoning. The irony is evident when you examine what German designers were prioritizing instead. They invested vast resources into developing more powerful radial engines, convinced that raw horsepower would overcome the theoretical advantages of liquid-cooled designs at high altitudes. The BMW 801 program alone consumed thousands of engineering hours and large amounts of strategic materials. Meanwhile, across the Channel, Rolls-Royce engineers were quietly solving problems the Germans hadn't yet realized would become critical. The Luftwaffe's technical staff fundamentally misunderstood the nature of modern air combat. The war wouldn't be decided by durability or simplicity, but at altitudes where air-cooled engines struggled to breathe, while liquid-cooled engines with proper supercharging continued to deliver full power. They had optimized for the wrong kind of war. By the time German engineers realized their mistake, British and American factories were producing Merlins at a rate that made any German response impossible. The engine they had dismissed as outdated in 1939 would continue to power frontline aircraft even when Germany surrendered in 1945, while many of their own superior radial engines had been abandoned as dead ends. To understand how this happened, we must return to Derby, to a factory that looked nothing like the gleaming facilities the Germans showcased in their propaganda. It was here that a small team of engineers spent years perfecting an engine design that would change everything. The Rolls-Royce factory in Derby didn't resemble the sleek, modern buildings German industry favored for propaganda photos. It was made up of soot-stained brick structures, housing workshops where machinists worked in conditions that would have horrified today's health inspectors. The floors were soaked in oil, heating was inadequate, and the constant screech of lathes shaping aluminum filled the air. Yet within these humble walls, Ernest Hives and his engineering team were conducting a masterclass in applied thermodynamics. Hives himself didn't fit the heroic engineer stereotype. Bald and always dressed in a worn three-piece suit, he had risen through Rolls-Royce as a test driver before becoming works manager. His genius lay in his methodical improvement, taking an engine design that worked adequately and refining it until it performed brilliantly. When Hives recruited Stanley Hooker from the Admiralty in 1938, he added the final piece to a puzzle the Germans never quite understood. Hooker brought something desperately needed by the aviation industry: proper mathematical rigor in supercharger design. Before his arrival, superchargers were developed through trial and error. Build, test, modify, and test again. Hooker approached the issue with pure fluid dynamics, calculating precisely how air molecules behaved when compressed, how temperature changes affected density, and how blade geometry impacted efficiency. Influence on efficiency. His equations predicted performance before a single test engine ran. The supercharger itself had a deceptively simple design. A turbine powered by the engine's crankshaft compressed incoming air before it entered the cylinders. Denser air allowed for more oxygen molecules per combustion cycle, enabling more fuel to burn and thus generating more power. While every engine manufacturer understood this basic principle, what set Rolls-Royce apart was their understanding of the secondary effects others ignored. For instance, German engineers knew that supercharging generated heat. Compressed air naturally heats up. Their solution was often brute force. Use stronger materials to withstand higher temperatures and accept the efficiency losses. Hooker's approach was entirely different. He calculated that cooling the compressed air before it entered the cylinders would further increase its density, effectively providing free additional power. The intercooler system he designed recaptured energy that German engines wasted as heat. More critically, Hooker and his team understood something about high-altitude performance that many contemporaries missed. As an aircraft climbs, atmospheric pressure drops significantly. At 20,000 feet, the air pressure is about half of sea level. A single-stage supercharger could compensate up to a point, but there's a limit beyond which it becomes thermodynamically inefficient. The air heats up too much during compression, losing the density gains. The solution was a two-stage supercharger, with the second stage compressing already compressed air. An intercooler between the stages removed the excess heat. The result was an engine that maintained sea-level power output at altitudes where German single-stage engines could only manage about 60% of their rated power. This was no minor advantage. In combat, the aircraft that can perform well at higher altitudes dictates the terms of engagement. By 1940, Hives had transformed the Merlin from a capable engine producing just over 1,000 Tonnenturds horsepower to a monster capable of nearly 2,000 horsepower at altitudes where most engines barely functioned. This transformation didn't come from radical redesigns, but from a deeper understanding of physics than anyone else had. The Derby workshops had become a laboratory where theory and practice came together in ways that would later prove devastating to German assumptions about air superiority. The ethylene glycol in the Merlin's cooling system was more than just a way to prevent overheating. It was essential to performance in ways that air-cooled designs couldn't replicate. To understand why, we need to look at the physics that German engineers chose to ignore. An air-cooled radial engine cools itself through direct exposure to airflow. Fins on the cylinder heads increase surface area, and the propeller's slipstream carries away the heat. It's simple and elegant, which explains its appeal to Luftwaffe designers. However, simplicity comes with a major limitation. Cooling efficiency depends entirely on airflow speed and ambient temperature. At 30,000 feet, where the air is thin and extremely cold, cooling might seem ideal, but it's more complex than that. The thin air means fewer molecules are passing over the fins per second, significantly reducing heat transfer. Liquid cooling overcomes this limitation. Ethylene glycol, chosen over water for its higher boiling point and lower freezing point, absorbs heat from the cylinder heads and transfers it to a radiator, where the heat is then carried away by the airstream. The real advantage is control. Engineers could place radiators in the most effective locations, design them for specific heat loads, and maintain consistent engine temperatures regardless of altitude or environmental conditions. A Merlin at 25,000 feet maintained nearly identical operating temperatures to one at sea level. This temperature stability was crucial for supercharging. Hooker's two-stage system generated massive amounts of heat during compression. Each stage could raise the air temperature by 70 or 80 degrees Celsius. Without effective cooling between stages, the air would become so hot that its density would decrease, negating much of the pressure gain. The Merlin's liquid cooling system allowed the placement of intercoolers that used the same glycol circuit to extract this heat. The compressed, cooled air entering the cylinders was denser than anything a single-stage air-cooled engine could achieve. German engineers eventually realized the problem, but their solutions came too late and were imperfect. The Junkers Jumo 213, introduced in 1944, attempted to match Merlin's altitude performance with a complex single-stage supercharger and after-cooling system. It was an impressive piece of engineering, but physics imposed constraints that German ingenuity couldn't overcome. A radial engine's cylinders must be exposed to airflow for cooling, creating aerodynamic drag. The more power you generate, the more heat you must dissipate, requiring larger fins, more drag, or accepting higher operating temperatures, which reduce reliability and power output. The Focke-Wulf FW190D, powered by the Jumo 213, demonstrated the potential and limits of this approach. It was fast at medium altitudes, but above 25,000 feet, its performance diminished. Performance dropped noticeably. Pilots noted that while the aircraft was formidable below 20,000 feet, encounters with late-model Spitfires or Mustangs at higher altitudes almost always favored the enemy. The liquid-cooled Merlin in these Allied fighters maintained power well into the upper atmosphere. By 1943, the gap in altitude performance had become a major problem for Germany. Allied bombers were operating at heights where Luftwaffe interceptors struggled to reach. The Bf 109G, with its pressurized cockpit and the latest Daimler-Benz DB 605 engine, still couldn't match the Merlin's performance above 28,000 feet. German fighter pilots learned to attack from below whenever possible, using the altitude advantage that Allied escorts could maintain with ease. Technical reports from this time revealed German frustration. While they acknowledged that liquid-cooled engines had superior high-altitude performance, Germany's industrial situation made it impossible to replicate the Allied approach. They had committed to radial and air-cooled inline engines. Their production lines were already set up for these designs, and changing would have required months of retooling they couldn't afford. The summer of 1940 brought the harsh reality that no wind tunnel or test bench could replicate. Over Kent and Sussex, theoretical debates about engine design turned into life-and-death struggles at altitudes where engineering mistakes didn't just lead to data for improvement. They meant failure to return home. Fighter command pilots discovered something Luftwaffe intelligence had failed to predict. The Spitfire's Merlin engine gave them options German fighters simply couldn't match. Flight Lieutenant Alan Deere, flying with 54 Squadron from Hornchurch, described an engagement over Dover where the altitude advantage proved decisive. His squadron had climbed to 26,000 feet before the raid arrived, a height that the Bf 109Es could reach, but not while maintaining the energy reserves needed for combat maneuvers. When Deere's flight dove on the German formation, the Messerschmitts that tried to climb away found their engines struggling in the thin air, while the Merlin-powered Spitfires maintained full power. This shouldn't have been possible according to German pre-war assessments. The Bf 109 had flown combat missions over Spain in 1937, 3 years before the Spitfire entered squadron service. Messerschmitt's engineers had refined the 109 through actual warfare, while Supermarine was still conducting prototype trials. The 109 featured fuel injection that prevented engine stalls during negative G maneuvers, a significant advantage over the Merlin's float carburetors, which would momentarily starve for fuel during steep dives. German pilots exploited this advantage, pushing into aggressive dives, knowing Spitfire pilots couldn't immediately follow without their engines sputtering. Yet, for all these advantages, German fighter pilots encountered a troubling reality. Above 20,000 feet, the Spitfire was their equal, or better. Combat reports from Luftwaffe headquarters made uncomfortable reading. Hauptmann Helmut Wick, one of Germany's leading aces, noted after an August engagement that British fighters maintained pursuit to altitudes where his own aircraft began losing responsiveness. Squadron records showed German formations becoming increasingly reluctant to operate above 25,000 feet without a significant altitude advantage. The Hurricane, often overshadowed by its more glamorous counterpart, also proved problematic for German calculations. It was slower than the Bf-109 and less maneuverable than the Spitfire, yet it destroyed more Luftwaffe aircraft during the Battle of Britain than any other fighter. The Merlin's reliability played a crucial role here. Hurricane pilots could push their engines hard during extended combat without the mechanical failures that plagued early DB601 engines. German maintenance crews reported connecting rod failures and supercharger bearing problems at rates that alarmed technical staff. What really undermined German confidence was the Merlin's potential for further development. Between July and October 1940, Rolls-Royce introduced the Merlin 60, featuring an improved supercharger that increased power output by over 200 horsepower. Squadrons received these upgraded engines while the battle was still raging. The Bf-109E4, on the other hand, represented the limits of what its DB601A engine could deliver. Further improvements would require the entirely new DB601E, which wouldn't reach squadrons until 1941. British pilots also benefited from better fuel quality that German engineers hadn't considered. The 100-octane aviation petrol supplied in large quantities by American refineries allowed for higher boost pressures without detonation. German fighters, by contrast, used 87-octane fuel throughout 1940, limiting their engines' power output. When Luftwaffe technical officers examined captured Spitfires, they found boost settings that would have destroyed a DB601 in minutes. The Merlin, designed with proper detonation margins and better cooling, handled these higher pressures easily. By September, the pattern was clear. The supposedly outdated liquid-cooled engine was outperforming its air-cooled and fuel-injected German counterparts in sustained combat at operational altitudes. North. American Aviation's Englewood factory received a request in October 1940 that seemed almost insulting. Could they design and build a completely new fighter aircraft in just 120 days? North American's response, delivering the prototype NA-73X in only 117 days, was an extraordinary achievement in aircraft design. However, what nobody realized at the time was that they had built an airframe of exceptional quality, but paired it with the wrong engine. The Allison V1710 engine seemed like a logical choice. It was American-made, readily available, and produced decent power at sea level. The Army Air Corps had successfully used it in the P-40 Warhawk, so North American engineers had no reason to question its suitability. But when the first Mustang reached RAF squadrons in April 1942, pilots quickly recognized that they were flying something special. The laminar flow wing design produced lower drag than other contemporary fighters. The visibility from the bubble canopy was excellent, and at altitudes below 15,000 feet, the aircraft was incredibly fast. However, problems became evident when pilots tried to climb higher. Above 18,000 feet, the Allison engine's single-stage supercharger simply couldn't keep up. The engine had been optimized for low-altitude operations like ground attack and reconnaissance, but it had never been intended for high-altitude air superiority fighting. RAF test pilots at Boscombe Down filed reports stating that the Mustang's performance above 20,000 feet was inadequate for modern combat. The aircraft that could outrun a Bf-109 at 10,000 feet was a liability at 25,000 feet. In April 1942, Ronald Harker, a Rolls-Royce test pilot with the RAF, flew a Mustang and quickly realized what others had missed. The airframe was brilliant, but the engine was wrong. He sent a memo to Rolls-Royce suggesting that fitting a Merlin engine would transform the aircraft. The response from Darby was cautiously enthusiastic. While they had Merlins to spare, the question remained whether the American airframe could accept a British engine without extensive redesign. The first conversion was almost casual. 4 Mustangs were taken out of service and sent to Rolls-Royce's Hucknall facility, where engineers began the delicate process of fitting a Merlin 61 into an airframe designed for a different engine entirely. The installation required new engine mounts, modified cooling systems, and a complete redesign of the cowling. When the first converted aircraft flew in October 1942, the test pilot's report contained one word underlined 3 times: remarkable. The transformation was astonishing. The Merlin 61, with its 2-stage supercharger, allowed the Mustang to maintain full power well beyond 30,000 feet. The top speed increased by 50 miles per hour at altitude, and the rate of climb improved dramatically. Most importantly, the aircraft could now escort bombers deep into Germany and return, something no other Allied fighter could achieve. With drop tanks, the Mustang's combat radius exceeded 1,000 miles, twice what a Spitfire could manage. American production lines quickly switched to the Merlin-powered design, and Packard, which was building the Merlin under license in Detroit, supplied engines while North American retooled for the P-51B variant. By December 1943, Mustangs were escorting 8th Air Force bombers over Germany, and Luftwaffe pilots were discovering that the Americans had fielded a fighter that combined range, altitude performance, and speed in ways no German aircraft could match. The Bf-109G and FW-190A, formidable against P-47s and P-38s, found themselves outclassed by an aircraft that shouldn't have existed. An American airframe powered by a British engine that German engineers had dismissed as obsolete. The Merlin's transformation of the Mustang was just one example of how versatile the engine was across many Allied aircraft programs. By the end of the war, 38 distinct aircraft types had flown with Merlin variants, a number that is even more impressive when you consider that each type often had multiple sub-variants with different engine marks. No other power plant in aviation history had such versatility. The Merlin's scalability was most dramatically demonstrated in the heavy bombers. The Lancaster, one of Britain's most successful bombers, mounted 4 Merlin XX engines, generating a combined 6,400 horsepower. Each engine operated independently, yet identically, simplifying maintenance and spare parts logistics. Ground crews could swap engines between aircraft without special modifications. This interchangeability extended across variants. Merlins from a Halifax could, with minimal adaptation, power a Mosquito. German logistics officers would have gladly traded vital organs for such flexibility. The Mosquito itself exemplified what Merlin power enabled. De Havilland's wooden wonder carried no defensive armament, relying entirely on speed for survival. 2 Merlin 21 engines gave the bomber variant enough power to outrun most German fighters while carrying a 2,000-pound bomb load to Berlin and back. Fighter variants with Merlin, 25 engines hunted German night fighters over occupied Europe, and photo reconnaissance versions with Merlin 77 engines flew so high that interception was virtually impossible. One airframe, multiple roles, all enabled by choosing the right engine variant for each mission. Across the Atlantic, Packard's production lines in Detroit churned out V1650 Merlins, the American designation for the engine that powered not just Mustangs, but also P-40Fs, Canadian-built Hurricanes, and even experimental variants of aircraft originally designed for other engines. The Curtiss P-40, which had been mediocre with its Allison engine, became genuinely competitive with the Merlin. The transformation wasn't as dramatic as the Mustangs, but the P-40's useful service life was extended by 2 years when fitted with a Packard Merlin. Naval variants presented their own challenges and solutions. The Ferry Barracuda torpedo bomber was fitted with a specially modified Merlin 30, designed to withstand the corrosive saltwater environment and violent catapult launches from carrier decks. The Ferry Firefly fighter used a low-altitude optimized Merlin 30 that sacrificed high-altitude performance for maximum power below 10,000 feet, precisely what carrier operations required. Each variant represented careful engineering to match the engine's characteristics to operational needs. This contrasts with German engine programs. The DB601 and its successor, the DB605, primarily powered variants of the Bf109 and Bf110. The BMW 801 was used in the FW190 and Junkers J88, while the Jumo 211 powered various bombers. Each engine was optimized for specific applications, with limited cross-compatibility. When production issues arose, German aircraft manufacturers couldn't easily swap engines without extensive redesigns. A bomber line waiting for Jumo 211 engines couldn't simply use BMW 801s without major modifications. The strategic implications were significant. Allied air forces could consolidate maintenance training, simplify spare parts supply chains, and achieve economies of scale, which Germany couldn't match. A mechanic trained on a Lancaster Merlin could work on Mustangs or Mosquitoes with minimal additional training. In contrast, a technician qualified on DB605s would be useless when assigned to a unit with FW190s powered by BMW 801s. The Germans operated effectively multiple parallel air forces, each with unique training and logistical needs. By 1944, Merlin production exceeded 30,000 engines annually across British and American factories. The Germans were producing only about 12,000 engines across all types and were struggling. To meet even that reduced target as Allied bombing crippled their manufacturing capacity. Those 12,000 German engines reflected not only lower production, but increasing compromises in metallurgy, design integrity, and manufacturing quality. The progression from the DB601 to the DB605 and then to the late-war Jumo 213 tells a story of diminishing options and mounting crisis that Rolls-Royce's methodical development approach never faced. The DB601, introduced in 1937, was an excellent engine that powered the Bf109E during the Battle of Britain and established German fighters as formidable opponents. But excellence in 1937 became obsolescence by 1943, and upgrading the design revealed limitations that Rolls-Royce's careful, continuous improvements had avoided. The DB605, introduced in 1942 as the successor to the 601, increased displacement and boosted power to 1,405 horsepower. It should have been a straightforward development. However, it became a nightmare, plagued by connecting rod failures, supercharger problems, and cooling issues. The root cause was materials. Daimler-Benz engineers had designed the DB605 assuming continued access to key materials like molybdenum, nickel, and chromium. By 1942, these materials were becoming scarce. Substitute alloys couldn't handle the increased pressures, leading to cracked crankshafts and premature supercharger bearing failures. Luftwaffe maintenance records from the Eastern Front paint a grim picture, with entire squadrons grounded awaiting replacement engines. Serviceable airframes sat idle because their power plants had failed. As production quality deteriorated, factories increasingly relied on forced labor and relocated to bomb-proof facilities, where maintaining pre-war standards became impossible. Engines left the factories with tolerances that would have been rejected in 1939. They reached operational units with known defects because rejecting them meant keeping squadrons grounded, while bombers ravaged German cities. Junkers. Motoren attempted to bypass these issues with the Jumo 213, an entirely new design intended to match or exceed the Merlin's high-altitude performance. On paper, it succeeded, with 1,800 horsepower and effective operation above 30,000 feet. It also featured sophisticated intercooling, approaching the efficiency of the Merlin's two-stage supercharger using a single-stage supercharger. In practice, however, the 213 arrived too late, and in too few numbers to make a difference. Development consumed years, delaying production until the autumn of 1944. By then, Germany was already losing the war, and even successful new engine designs couldn't reverse the strategic defeat. The broader German engine program had trapped itself in a corner. They developed excellent designs. The BMW 801D was genuinely world-class, and the DB605 with a larger supercharger nearly matched Merlin's altitude performance. But nearly wasn't enough. World-class designs meant nothing if you couldn't produce them in sufficient numbers with proper materials. Luftwaffe fighter strength peaked at roughly 2,300 aircraft in the summer of 1944. The 8th Air Force alone could deploy more four-engine bombers, each powered by 4 Merlins, on a single mission than the Luftwaffe could field in a day. Design philosophy played a major role in this disparity. German engines prioritized short overhaul intervals, typically 100 hours between major overhauls, compared to 300 hours for the Merlin. This reflected different operational assumptions. German fighters, operating from Reich air bases, could return for maintenance frequently, while Allied aircraft, often operating from distant bases or crossing the Channel, needed reliability measured in hundreds of flight hours. The German approach worked well when they controlled their maintenance infrastructure and had spare engines available. But it collapsed when Allied bombing destroyed overhaul facilities and replacement engines stopped arriving. By 1945, Luftwaffe units were cannibalizing 3 damaged aircraft to produce 1 serviceable machine. Meanwhile, Merlin production lines were slowing down, not due to disruption, but because Allied victory was assured and post-war capacity could be scaled back. The Ford Motor Company's Rouge plant in Dearborn, Michigan, had spent the 1930s perfecting assembly line techniques that made automobile production a precise science. When the Packard Motor Car Company received the license to produce Merlins in 1940, they consulted Ford engineers about adapting these mass production methods to aircraft engine manufacturing. What emerged was an industrial system that turned precision engineering into a commodity and fundamentally changed how wars could be won. Traditional engine manufacturing, as practiced at Rolls-Royce Derby, was essentially sophisticated craftsmanship on a larger scale. Skilled machinists produced components with exacting tolerances. Fitters hand-assembled engines, and inspectors verified each unit individually. This method worked for producing 500 engines per month, but it couldn't meet the demands of wartime production. Packard's challenge was transforming the Merlin from a craftsman's masterpiece into something that could roll off production lines like Model T, Ford's. The solution required rethinking manufacturing from scratch. Packard engineers developed detailed tolerance specifications for each component, determining which measurements were essential for performance and which were unnecessarily tight. They found that Rolls-Royce's drawings sometimes specified tolerances finer than necessary, not due to engineering needs, but because of British manufacturing tradition. By relaxing non-critical tolerances slightly and tightening the truly important ones, Packard created parts that were easier to manufacture and more consistently interchangeable. Specialized machine tools replaced skilled manual labor wherever possible. A master machinist at Derby might spend 40 minutes hand-fitting a connecting rod to achieve proper clearances. Packard designed dedicated fixtures that held the rod precisely, while automated cutters achieved the same result in just 4 minutes. The machinist's skill wasn't eliminated. It was encoded into the tooling itself. One skilled worker could now supervise multiple machines, each producing identical components. By mid-1943, Packard's production tempo reached 27 Merlins every hour, 648 engines per day, working around the clock. The numbers are staggering. That's more engines in one day than Rolls-Royce Derby produced in its best pre-war month. It's equivalent to the entire German aviation engine industry's weekly output. Every 12 days, Packard produced more Merlins than Germany manufactured DB605s annually. This wasn't simply about working faster or hiring more people. It was about systematically eliminating inefficiencies and manual operations. The result was engines that cost roughly half of what British-built Merlins cost, despite American workers earning higher wages. And they were reliable. Durability tests showed that Packard Merlins met or exceeded Rolls-Royce's reliability standards. Ford's contribution extended beyond direct engine production. Their experience with supply chain management revolutionized how Packard sourced components. Instead of relying on a few suppliers producing complete subassemblies, Ford's methods spread production across hundreds of smaller manufacturers, each producing simple parts to exact specifications. A workshop that couldn't build an entire carburetor could still stamp out carburetor bodies by the thousand. This distributed manufacturing was remarkably resistant to disruption. Losing one supplier barely affected overall production. In contrast, a single successful Allied raid on the Ehler Maschinenbau plant in Leipzig in October 1943 reduced German fighter production by 12% for 6 months. The facility produced wings for Bf-109s, and there were no alternate suppliers that could quickly scale up. When Allied bombers struck ball-bearing plants in Schweinfurt, Luftwaffe engine production plummeted because there were only a few factories in Germany capable of producing aviation-grade bearings to the required specifications. American industry had made Merlin production virtually indestructible through redundancy. You couldn't bomb Merlin production into submission because it wasn't dependent on just one factory, or even a dozen. It involved hundreds of facilities across 2 continents, each contributing pieces to a robust industrial system. The machine that just kept accelerating. Victory in Europe Day, May 8, 1945, marked the end of German aviation engine development. Within months, BMW facilities fell silent. Daimler-Benz switched to producing whatever Allied occupation authorities allowed, and Junkers Motoren ceased to exist as a functioning entity. The engines that were meant to represent the future of aviation became instant museum pieces. Meanwhile, the Merlin, once considered an outdated relic from 1930s thinking, was just beginning its second life. RAF Fighter Command continued flying Merlin-powered Spitfires until 1954, 9 years after the war ended. These weren't just museum pieces kept flying for nostalgic reasons. They were still frontline fighters, although they were increasingly relegated to reserve squadrons as jets took over primary duties. The final operational Spitfire sortie took place in Malaya during the emergency, where the Merlin's reliability was valued more than jet speed in jungle and counterinsurgency operations. Pilots reported that Spitfires were still in action when newer jets were grounded due to technical problems. The Lancaster continued even longer. Coastal Command operated Lancaster maritime patrol variants until 1956, hunting Soviet submarines in the same waters where they had tracked U-boats a decade earlier. The 4 Merlin engines proved perfect for long patrols, requiring 12–14 hours of flight time, a feat jet engines of the era couldn't match. In 1948, Argentina purchased Lancasters and operated them into the early 1960s, making the Lancaster arguably the last piston-engine bomber in frontline service anywhere in the world. Civil aviation embraced the Merlin with equal enthusiasm. Hundreds of surplus Lancasters, Mosquitoes, and other military aircraft were converted for civilian use. Trans-Canada Airlines flew Merlin-powered planes on domestic routes until 1963, and British European Airways operated Merlin-powered aircraft on European services throughout the 1950s. These weren't just romantic relics. Airlines continued using them because operational costs were competitive with early turboprops, and the Merlin's maturity meant fewer unexpected maintenance issues than newer engines. The racing world discovered that a well-tuned Merlin could produce astonishing power outputs. Unlimited air racing, which resumed after the war, became dominated by heavily modified P-51s and Spitfires, pushing the Merlin to 3,000 horsepower and beyond. These engines were producing double their original design output. While they didn't last long at these extreme levels, the fact that they ran at all was a testament to the strength of the Merlin's design. No DB605 or BMW 801 could have survived such abuse. Perhaps most notably, when Britain needed a stopgap fighter in the late 1940s while jet development continued, they chose to design around the Merlin. The de Havilland Hornet, which entered service in 1946, mounted two Merlins and remained in operation until 1956. It wasn't just a wartime design pressed into continued service. It was a completely new aircraft, deliberately designed around an engine that German engineers had dismissed as obsolete. Even the Merlin's industrial legacy persisted. The mass production techniques Packard developed for Merlin manufacturing influenced post-war automotive engineering. The quality control systems, the distributed manufacturing networks, and the statistical process control methods all became standard industrial practices. By contrast, German aviation engine manufacturing left behind primarily cautionary tales about what happens when you optimize for the wrong variables. By the time the last operational Merlin-powered aircraft retired in the mid-1960s, the engine had logged more service hours than all Luftwaffe power plants combined. The outdated design that German engineers dismissed in 1939 had outlasted not only its supposed superiors, but also entire generations of aviation technology. It had powered more aircraft types, equipped more air forces, and served longer than any other aircraft engine in history. And it had done all of this while remaining fundamentally the same design that Ernest Hives and Stanley perfected in that humble Derby factory so many years before.